Leetcode solution. If you want the best mock interview experience in North America, feel free to check us out at baozitraining.org. We're here to help you land your next big offer. Today, actually, I have a confession to make. So I was looking at this problem called a course schedule. Apparently, I recorded this video like 5 years ago using BFS, and then there's also another solution using DFS. So I have to confess because, see, at that time, I think what I was doing is more like I want to do real-time coding. So it's kind of like I was coding along the way, and I was thinking it's a very real experience. But it's not really contains lots of explanation. So like this guy RK was saying, no real explanations, thus all the dislikes. Well, it's true. Could you well, I like my own videos if you haven't noticed. Could you re-record another one explaining how you use the queue, why, what is the logic of BFS for this solution? Well, it is a topological sort using BFS with the queue. Otherwise, it is just one of live coding videos. Thanks. I think RK, you made a really good point. So that's why I'm recording this one for you as well. Why this code costs TLE? I don't think so. You think fast and type fast. Thanks. 为什么 request 来的保证返回 true 呢? Yeah. And for the DFS one, to be honest, for any kind of like a topological sort or dependency graph, DFS I want to explain because I want everyone who is lead coding know it's not about the quantity of the problem, it's about the quality of each problem. Can you solve each problem using different ways? So that's why I also introduced a DFS solution, which I will also talk about today, but I think Shanshan Li made a very good point. Why not first make a clear explanation and then code? Yeah, I think I didn't really explain and then started coding. This is also a no-no, to be honest, in real interview. Like, never ever directly jump into coding. Okay, so that was 5 years ago me kind of doing this, and today I'm going to hopefully made up for this. So 5 years later. So the problem that you should already know. So given a dependency graph, essentially the problem is how do you detect whether there's a cycle in the dependency graph or not? I think when I was coding, in the problem, they say, okay, if you take course 0, you have to first take course 1. This is more like course 0 depends on course 1. So yeah, I think that is how it works. If you reverse everything, like 1 depends on 0, then you have to reverse everything again. It's neat. Anyways, so the problem, the thought process is this is a very classy dependency graph problem. And what we can do is we translate this problem into given a directed graph if there is a cycle or not. A textbook solution is using this Kang's algorithm for topological sort. And then for this problem is you only need to answer yes or no. You don't need to give a topological sort order. But if you need the order along while you are traversing this graph in BFS order, then you can have an extra array to record those orders. So there's a few ways to code this problem up, but now here's the explanation, right? So if you have this graph, for example, like course 0 depends on 1, so it reads as it depends on, and then 1 depends on 3. So given this graph, and I drew a blue line. This is like there's a circle. So for this particular graph, we should actually return false because there's a circle. So the basic idea is actually very simple. So first, you need to build a graph. How do you build a graph? For this particular problems, there's actually 2 ways to build a graph. Remember, the first way I coded up, to be honest, it is a little bit overkill for this program because you define a node, you have each value of the node, and then you contain a list of nodes using neighbors, and then you have a constructor looks like this. So this is a very universal way. So nowadays I like it more because it does takes you like maybe extra 20 seconds to type this out, but this can be extended to solve essentially all the BFS problems or all the problems using a graph with this adjacency matrix way. So so far, if you haven't know, you should look at my previous videos. There's 3 ways you can represent a graph, right? There's a adjacency matrix, which essentially giving you a matrix, node 0, 1, 2, node 0, 1, 2. If there is a edge between this node, you check 1, yes, yes, yes. It's a very sparse matrix, as you can tell. Another way is called there's basically a linked edge list way. So if there's a node 1 and 2 have a have a so for example, if you have 0 and 1, you have a edge between this, you will have a 0 and a 1, and then you have a 1 and a 3, that kind of thing. So using all the edge, it's not that common. So the most common way is using a they call it adjacency list way, which essentially of 0, all its neighbors is 1 and 2. So if it's a direct graph like this one, that's it. But if it's not a directed graph, if 0 has an edge with 1, and then 1 should contain a neighbors at 0. So it's a kind of like it's a mirror, right? So one way to represent this graph for me is I can use a node, like it looks like this. And then the first step is I build a graph. So you can look at the code. So this is how I build a graph. Essentially create a new node for everything, and then add the dependency, add the neighbors. And then at the end of the day, I return a graph. Essentially is a list of nodes. So this is how you represent normally a graph. What is a graph? It's basically a list of nodes, right? And then I'm pretty much using topological sort to check whether, actually this might be a better code. So first do some sanity checks. This is relatively trivial. It's like, oh, if you only have one course or you don't have any prerequisite, you can complete it. And then you build a graph. And now this is the algorithm part. This is relatively simple. The way it works is after you build this graph, so you start with all the nodes that has no neighbors. So this is essentially your topological sort. This is your topological order, the first level. So in this particular graph, you will have a node 4. So you put it into your queue. And then while this queue is empty, you always pop in this node, and then you find, okay, who depends on this? Because now you are going to finish this course, right? And then you see, okay, after removing this node from all the other nodes, is there any node that the neighbor is 0, which means there's no circular dependency? So in this case, it's 2. So you put 2 into the queue. So 4 is already out of the queue. And then you're doing the same thing. Who has basically a dependency of 2? And then you say, okay, 0. So what you're gonna do is you're gonna remove 2, and then you're gonna check. You're gonna remove this line. Is there any nodes in this graph that has a neighbor? Essentially means dependency is 0. Neighbor size is 0. No. So this is why this graph has a cycle. So if this graph doesn't have this line, you will see, oh, there's actually 3. But 3, you can actually push in 3. So this is the way this algorithm works. Given this, first you add the node, and then you have this queue. And then what you need to do is you check, oh, if there's any neighbors contains this node. If there's a neighbors contains this node, you remove this neighbor from this node from the neighbors. And then you only in-queue this when the neighbor size is 0. So this is pretty much the way it is. And then at the end of the day, you see, okay, did I visit all the nodes? If not, then that means there's a circle, or else it's actually no circle. So for this particular case, you only visit like 2 nodes instead of 5 in total. So you return false. It's a very clean way for topological sort. If you want to record the order, you can have a list to record all the orders you visited, like you first visited 4 and then 2 along the way. Very similar to this. So let's talk about the time and space complexity actually. So the time complexity of this is OV because you visited each vertex once, and the space complexity is actually this is V plus E because using adjacency matrix, you will need to carry the node and also you need to carry the edge in your list. So it's OV plus E. It's still kind of linear. Another way is a super simple tweak using hash map. The code looks exactly almost the same. The only difference is this is what I coded 5 years ago, is initialize it first and then doing the same BFS thing. So this is also very similar. It's like, if the dependency size is 0, this is when you actually offer or add the node into the queue, and then you minus the course remaining, and then later on you check whether it's equal to 0 or not. The only difference between this and that is, as you can see, I didn't define a node and then the node class or node struct, whether you call it. So the way I represent this is I just simply use a hash map. Key is the integer, is the node, and then each node contains the neighbors as a set. So it's kind of a shortcut or a hack for this problem, but definitely it's enough suffice for this problem. Just represent a graph like this versus you represent a graph actually like a list of nodes, and then each node contains a value and its neighbors. It will render the same time and the space complexity. The space complexity is just OV because you use a hash map, number of vertices. And then previously, as you can see, I talked about how to solve this in DFS. It's not that straightforward, but it's still straightforward. But normally, I wouldn't use DFS for any kind of topological sort because it's not guaranteeing you the topological order. It just for this problem, if you just purely detect the circle, it actually can be done. So the way it works is actually, so let's say this is the graph. So the way it works is for DFS is you just keep, as long as you have one node, you just keep a recursion. You have node 1 and you will have node 3. So essentially you go through all these children, right? And then you have 4 and then you have 5, everything is good. And now you increase it back to 1 is good, you increase it back to 2. And then you started your another set of recursion. So now you are basically at your node 2 and then you recursion to node 3 and then doing 4, 5, recursive back. One thing is we all remember in recursive call, you can have a lookup or memorization. So it's like, oh, if I already visited 3, so I don't need to do this whole calculation like this part again. So I can directly return, oh, there's no circle, I already checked, and then you return it back. So if you translate that into code, is still represent a graph like this. And then you have a helper method called explore. Explore, I will have a lookup table. This is basically the global lookup table, which essentially is like your memorization. So once you're at the node 3, again, you don't need to redo the whole thing afterwards. You can directly return. And also what you need to do is for each of the dependencies, you check whether it's visited or not. If it's already visited, so this visited is in your recursion step, you keep a visited array. If you already visited, means there's a loop. You return, or else you just continue the recursion. And then here is basically you reset your visited max, visited array. And then this is, okay, this vertex, there's no circle. So what it means is this visited, you keep it visited in your recursion function like this, in this order. Take a look. I mean, it will work. Even without the lookup, it will work. It's just more computation, right? Because you calculate everything again. Cool. The time complexity of this is still O of V given this method because I keep a memorization. So it didn't result in an exponential way recalculating. And the space complexity is OV because you need a lookup hash map for memorization purpose. I also linked the official LeetCode solution in the link, so you can take a look. And yeah, the geek score for geeks, this explains the topological sort as I explained. You only include the node when what they call it, like the income degree is 0, which means the dependency is 0. All right, hopefully this will meet up to you guys for the 5 years ago. I apologize for that. And yeah, leave any comments. Any comments are good comments, or like or dislike. Let me know what you think. Until then, I'll see you guys next time. Take care. Bye.